In this video, we're going to take a look at the binary search algorithm. So in one of my previous videos, we looked at the linear search algorithm and saw how it worked and also coded up an implementation of it in C++. So with linear search, we didn't have any sort of preconditions. We didn't have to have a sorted array. In the case of binary search, we do have to have a sorted array. So we do have that requirement. But the cool thing about binary search in comparison to linear search is we cut our search space in half on every single comparison. With linear search, if we had a 50,000 or 100,000 element array or maybe a million element array, we may have to do 50,000, 100,000, a million comparisons before we find the value that we're looking for, because it may be at the very end of our array, or it may not even be in the array at all, and we've done all those comparisons before we find that out. That's not the case with binary search. So with binary search, with a 50,000 element array, after the first comparison, if the thing that we were looking for didn't match on that first comparison, then it would eliminate half of the search space. So to give you a broad idea of what's going on with the binary search algorithm is that we find a midpoint value. So we're able to calculate that fairly easily since we're dealing with a sorted array. And we'll do a comparison between the value that we're searching for and that midpoint value and see if they're the same. If they're not the same, what happens is we're able to eliminate half of the search space at that point in time, either the bottom half or the top half, depending on if the value that we're looking for is greater than or less than the midpoint value. So let me show you how binary search works on this small array that we have here. So you can see that we have an 8-element array here, and it meets the precondition of being a sorted array. So all our values here are sorted in ascending order. And we'll say that we're searching for the value of 82. So I'll just say SV for search value, and the search value is going to be 82. And we can see the 82 exists in this array. It exists here at the second to the last element of our array. And the way the binary search works is it starts off by setting up a low and high value. The low is just going to be set up to hold the index of the very first element of our array. That's how it starts off. And the high would just be holding the very last index of our array. And then based off of low and high, we calculate a midpoint. So we just simply take the index value at high, add it to low, so this would be 7 plus 0, divide that by 2, which would be 3.5, and then truncate the fractional part since we don't have any fractional index values. So that would be 3. So our midpoint would be set here to 3. And now we do a comparison between this value here at the midpoint, which is 47, and our search value. And we see that those are not equal. And the next thing we do is check to see if our search value is greater than or less than the midpoint value. So if it turns out that the search value is in fact greater than our midpoint value, we're able to update our low value, and the low value would be updated to being one more than the midpoint, and then we would update our midpoint. Now if it turns out that the high value, just to kind of discuss what happens, we know that in our case the search value is in fact greater than the midpoint value. But if it was the case that, say we were looking for 22 instead of 82, so in that case we would find that the midpoint or the search value is in fact less than the midpoint, and we would end up updating high to being 1 less than the midpoint. Let's go ahead and update our low value to being 1 more than the midpoint. So I'll go ahead and indicate that the L, our low value, is going to be updated to being 1 more than the midpoint value. And then we'll update midpoint. So midpoint gets updated as well. So midpoint's going to be updated by taking the new low, which is 4, adding it to 7, which would be 11, and dividing that by 2, which would be 5.5. So we would now have midpoint setting at 5. Again, we chop off the fractional part, so we truncate that. So we'd have midpoint here at 5. And what we effectively have done after all that is eliminated half of our search space. So all of this business here is no longer in our search space because we have a new low and a new high. So the algorithm starts all over again. So we say that we do the comparison between what we have at midpoint, which would be 67 and 82, and we see that 82 is in fact greater than 67. So we're going to be updating low once again. So we'll have low being updated to being 1 more than the midpoint. So I'll indicate that low is being updated here to being 1 more than the midpoint. And then we would calculate the new midpoint. So midpoint would just be calculated by adding low and high, which is 13 in this case, and then dividing by 2, and that would be 6.5. We lop off or truncate the fractional part, so that would be 6. So we now have midpoint being 6, which is in this case the same as low, and that's perfectly okay for this algorithm. So midpoint is now here, and then we would do a comparison between the midpoint value, which is 82, and the search value, which is 82, and they're equal, so we're able to stop our search at that point in time. But you can see that we eliminated half of our search space once again. So this is really powerful in terms of the way that binary search works. And let's remember, just to kind of emphasize some of the main points, is that we do have this precondition that the array must be sorted. And the other thing is it cuts the search space in half after every single comparison, which is huge. Now, more formally, we would probably say that the performance of binary search, if we were looking at describing a function in terms of the amount of work required, the amount of comparisons, we'd say it has this log base 2 n performance, where n would be the number of elements that we have in our array. So in this case, we only had 8 elements in our array, but you could think of something really large, so maybe the 64,000 element array. So with a 64,000 element array, if you were doing log base 2 of 64,000, that would be around 16. And if you were to do log base 2 of double that, say 128,000, that'd only be 17 something. I don't know exactly what it would be, but it's around 17. So you'd only have to do really one more comparison if you doubled the search space. And that's really what's going on with binary search. We're able to double our search space and only have to do one more comparison to determine if the thing that we're looking for, or to find the thing that we're looking for, or to determine that the thing that we're looking for is not in the array. So let's go over to Eclipse now and code up our own version of binary search. Alright, so I'm over in Eclipse now, and I've already created a project, and also I've created a CPP file called binary search. And what I've done is copied the body of our main function from linear search. So in one of my previous videos we did a linear search algorithm, and I've just copied the body of the main function from that particular program into the main function here. And the only thing that I'm going to change up in this particular main function is our array. I'm going to make this array a sorted array, so we'll just use the same numbers that we used in the example that we did previously. So we'll say we have 12 and 22, let's see, 34, 47, 55, 67, let's see, what else do we have? Oops, I forgot a comma. Let's see, comma, and then we had 67, and then 82, and then also 98. And the other thing we'll change is just the number of elements in our array. So whenever we call binary search, so I guess I should change this here to binary search, since that'll be the name of our function. And we'll change this here to 8, since we have 8 elements in our array now. And the rest of this particular body of our main function from linear search that I've pasted over here into our binary search main function body will stay the same. So if you have any questions about how we developed the code associated with this main function, go and look at the linear search algorithm video, and I explain in detail sort of what we did here, and you can probably read through it and not have too much of a problem. Also, I should note that you can find a copy of this code from this video out on Pastebin. So if you look at the description, I'll have a link there to the URL on Pastebin where you can find this code. Okay, so let's go above the main function here and start writing the function definition for binary search. So this is going to be an int returning function, just like our linear search was an int returning function. So we're going to just return the int value that represents the index of where we found a particular search value. If we don't find it, we'll just return -1. So we'll have int as our return type, and the name of this particular function will just be binary search. And we'll pass in our formal parameters of an int array, and we'll pass in the size. So we'll say that that's int size, and we'll also pass in the search value. So the exact same formal parameters that we had for our linear search function. So if you remember from our discussion, we said that we needed to have a low and high value. So those were initialized, the low value was initialized to 0, and the high value is going to just be initialized to the last element, or the index of the last element of the array, which will just be size -1. So we'll have an int variable here called low that we'll set to 0, and another int variable called high that we will set to size -1. So that's our low and our high. Now, the next part here, I'm going to focus on really what we would do on a single iteration. So we continue doing the same operations over and over again. So I just want to focus in on what we're going to be doing on each iteration. We talked about being able to calculate this, this midpoint. So I'm going to declare a variable called mid here. And then below that, I'm going to calculate what mid is. So we'll say that mid is going to be equal to, we said that that was just simply low plus high, right? And then we divided that by 2. Now the cool thing is we're going to be doing integer division here. So low and high are both integers. 2 here is an int literal, so we have an int divided by an int. So we end up with integer division, and we're automatically lopping off, truncating that fractional part, which is exactly what we want to have in order to calculate the midpoint index value. So we get that, and then once we calculate the midpoint index value, we can start doing our comparison between our search value and the value that's there at the midpoint. So we can ask this question. We can say if the search value, so if our search value is equal to the value that we have at array mid, so basically what we're saying there is we're just checking what the value is there at the midpoint that we calculated. If that turns out to be the case, our search is over with, and we can just return mid at that point. Now, if that's not the case, we know that we either need to update low or high. So we'll have an else if here and say, well, if the search value turns out to be greater than array mid, so the value that we have there at the midpoint, then what we'll need to do is update low. So in that case, we'll update low to just being mid plus 1. And that was the case that we saw whenever we were searching for the value of, I think it was 82. So we were searching for 82, and we kept having to update low in that case. If that turns out not to be the case, we can just say else, because there's really nothing else to test. We'll update high, and high is just going to be updated to being mid minus 1. And that's pretty much it in terms of what we're going to be doing on each iteration. Now we got to think about the looping structure that we're going to have here. So we got to wrap up all this code that we just wrote here related to calculating the midpoint and then doing comparisons between the value at the midpoint and our search value to determine whether we found our value or if we need to update low or if we need to update high. So really this set of steps here keeps going on as long as the low value is less than or equal to the high value. As soon as the high value crosses over the low value or the low value crosses over the high value, we need to stop at that point because we now have exhausted the search space of our array. So what we're going to do here is just have a while loop here. So while that condition there is where we have low less than or equal to high, then we want to keep doing this operations or these set of operations here where we're updating the midpoint and then the value that we're looking for is not equal to the value there at the midpoint, either updating high or low. So let me just tab all that code over and put in a close brace there. And that's pretty much it in terms of our binary search, except for if it turns out that we don't find the thing that we're looking for, we still need to return a particular value. And so we'll return, let me create some spaces there so you guys can see that a little bit better. So we'll return -1. So that's it for binary search. So not too bad of a function in terms of the number of lines of code, and even the complexity of the algorithm is not that bad. So let's go ahead and build this and run it. So we'll go ahead and build it. Looks like everything built okay, and now we'll run it just to test everything out here. So we'll go ahead and enter in an integer. We'll enter in 82 just to see a value that's actually in the array. And we see that the number 82 was found at the element with index value of 6. And let's check that out. So 0, 1, 2, 3, 4, 5, 6. Yeah, so that's where 82 was found. Let's run it a couple more times. And we'll put in maybe the value of 22. And we can see that 22 was found at the element with index value of 1. And that is the case because this would be 0 and this would be 1. Let's put in a value that doesn't exist in our array, so we'll put in maybe the value of, let's see, 26, and we can see that 26 was not found. The other thing that I'd encourage you to do is, something I really want people to, I guess, embrace is this idea of using the debugger. So you may want to step through the code and see exactly what paths of execution is being taken in the binary search function as you put in different values. So that's it for this video.